All right, next up we have Sebastien visiting and telling us more about, I think, self-organization and brain tumors.
No. I can speak without the slide otherwise. But... Oh, thank you. So thank you for the organizer for the invitation and speaking here. So I apologize, I just arrived today because I'm at SU here, sorry. So we actually have the final week today, so it's kind of busy week for students waking up saying, oh, we need to work on the exam. So yeah, so I'm going to talk about oncostreams. So it's going to be like a follow-up about what Pedro talked about. Slightly different. I'm not going to talk about topological effect. I'm not yet that. So I'm like a mathematician. So usually Pedro is kind of like in the front line. I got to catch up with him with doing some interesting modeling. So here I'm going to talk about three things. So kind of like how we end up modeling oncostream mathematically. So how we can have those stream forming in two different directions and being nonetheless biologically relevant. So let's start actually with the first model we're gonna talk about. So diffusion on blood vessel. And before doing that, I just want to give you like a highlight about how we go with the collaboration with Pedro. So our goal here is I put here interesting glioblastoma, so I don't need to talk about it in front of this crowd here. But basically, the idea is to go from some experimental design. So Pedro is going to give me some data and try to do some modeling afterwards. And what my key role here, I'm trying always to derive macroscopic model. So we already have seen the talk this morning about that. So how we go from some agent-based models, so we're probably going to talk about more this afternoon, some equation related to how cells move. And now you get here to the so-called macroscopic scale. So how do you extract so-called PDE, partial differential equation. After which, of course, the goal will be to kind of get some idea about how the system evolved, get some therapeutic implication, but that's kind of like very hard. So my goal here, I'm just going to talk briefly about this step here to go from, I'm going to catch some data from Pedro and first some agent-based model and try to see what can we guess about the macroscopic behavior. So the first, I can skip this one here. So we already discussed about this morning. So the first type of experiment I'm going to look at here, so that's Pedro and Maria. So the experiment that we're trying to do here is to see how glioblastoma were actually invasive inside the brain of a mouse. But the idea was to see, like, because this is tumor cells, and how does it spread was not necessarily like a bubble, like you would see, like if you have a reaction diffusion model, but more like at first there is two phases, basically a phase we kind of explore. And after which, when they explore, then you have kind of like a bubble growth, meaning like you have the reaction diffusion type. So the idea was to say, but how can we model this type of phenomena here, kind of two phase? And the key idea here is that when you look deeper here, closer, you see that actually the tumor cells are not just spreading like a random walk if you want, they're actually like moving along the blood vessel. So here they really tend to attach to the blood vessel and to move along. So what's the goal here is just to say, okay, can you model that mathematically? So bring a very simple model. I'm not going to talk about parameter estimation or anything like that. Very basic model. Can you have something like this? You spread along blood vessel and then you grow. So the model here we end up playing around with. So this is kind of a sketch. So you have a tumor cells here. And what we decide to play with, so we have just like a cell moving around. So here, if you're familiar with the equation, that's kind of like correlated one-by-one work. So it's kind of a diffusion model, Brownian, but you have a direction. So you move a direction and you just put some noise in the direction you go. And then you kind of attract the blood vessel. So when you're going to go blood vessel, you move along here. And because of randomness, sometimes you exit. And if you don't find any blood vessel at one point, you're going to die. And if you're on blood vessel, you just divide. So you have a so-called Birch-Death process, and we already talked about that in this morning. So this is here. So the model, I'm not going to talk about too much about how to estimate the parameter, etc. But this is a rough first kind of simulation. So we start here with the same initial condition as we being given from the experiment. So that's the blood vessel, and this is the tumor. And you let it play. And what's nice here is that when you observe is that at first it's kind of spread around, it's kind of not so much concentration. So you move along blood vessels that guide actually kind of the diffusion. And after which you have the phase where like when they kind of settle here, the tumors start to grow. And if you look more like from a macroscopic perspective here, you will have this kind of two phase where they first like diffuse kind of, and then you have this kind of increasing here of the density. So very basic model, but we wanted to have just a starting point to see like, can we see how things go? Can we model that mathematically? So next question, for instance, would be like, what would be the macroscopic model for that? It's not very complicated here because there is one ingredient I haven't put here, and I'm going to focus on the second part here, no interaction. So every time you see a diffusion model, the typical diffusion, there's no reaction. You just suppose that the cell are actually just doing Brownian motion. Of course, that's not what's going to happen. They do interact for a simple reason that they cannot occupy the same space. So here's a key ingredient that's missing, and I'm going to just focus about this. Volume exclusion. So they cannot occupy the same space. What's going to happen here if I put that on top of it? So this is for the second part here. So I'm a mathematician, so I don't like my life complicated. I simplify as most as I can. So I just take the previous model here and I remove everything. So no blood vessel, no anything. Only what I care about, push each other out and some cell diffusion. As simple as that. So very like only two ingredients, you push and you divide. Question is, what's the macroscopic behavior for that? So think like, it could be some like reaction diffusion model as usual. Turn out, no, it's a little bit more complicated. So let me just show you some simulation just to show you like a brief idea. So this one here, I just, let's say standard case, if I can open, yes, okay. So this is just like a regular, so you push each other out and then you divide. So what you see here, so some cell randomly, one cell is gonna divide, and because you don't like to be like too much people around you, you push each other out. So very simple model, and you just, what you expect, kind of like a reaction diffusion type of. Where here, it's not really volume exclusion, because when a new cell's popping up, then it takes some time to push. So what I'm doing here in the second, same model, but I'm gonna crank up the pushing. So instead of just like pushing, you just literally like get out, okay? So I'm doing this simulation, I put in green because kind of like cells are Hulk. So you put Hulk and then you push everybody out. So no one is near me, okay? So if you do this kind of dynamics, so now same idea, but every time you have a new cells, immediately push each other out, okay? So very simple. But so let me just go a little bit after. So what's interesting here is that if you think about a macroscopic model, so think about like 1 million cells, it's kind of simple here because inside is always going to be the same. The density will be constant. I cannot have two cells on top of each other, so the density is constant. So what's happening here, all the dynamics is actually just what's happening here at the boundary. So I can have an idea about what should be the macroscopic model. It's not a reaction diffusion here, it should be a free boundary motion. So how the boundary is evolving there. So here, that's what I described here, there. So mathematically, you would like to use like this notation here. Omega is my domain. So derivative of my domain here, that's my, here's a circle here, can have an equation for that. So not a reaction diffusion again, because it's just constant and then boundary moves. What should be the equation? I'm going to skip the detail because it's not necessarily like super easy to get there, but let me give you the main idea. So you start with so-called macroscopic equation, call it agent-based model if you want. First step is to look like statistical description. So instead of looking at each cell, you look at the density. So it's relatively simple to derive from agent-based model to this equation here. You just typically you have a Brownian motion, you replace by a diffusion model. You have some derivative, is typically a transport equation. So you have some equation of this form. So this one here involves some convolution. And then you kind of try to zoom out. So you have to derive a macroscopic equation. You cannot just stay like that. You need to really zoom out. So here's the key, for instance, is to suppose that the radius of your cells gets smaller and smaller, so you can kind of zoom out to see what's happening there. And so if you get there, what you get instead of a convolution here, so-called diffusion. But let me point out here the key, for instance, that you have a square. So for those like familiar with diffusion, that means that's a porous media equation. So it's non-linear. It's not normal because you have interaction between cells. So you don't expect to have something a linear PD because that would be non-linear, no interaction. Another term here, okay, let me skip that. That's actually the diffusion only appears. So this, if you have a certain threshold. If there is almost no cells, you don't push each other out, so nothing happens. So diffusion here happens only if you pass a threshold of density, and that's why you're gonna have free boundary problem. No density, nothing. If you pass the density, boom, you start to push each other out. And what we get here, so we need to rescale again, but I'm gonna skip that. We get so-called Elisha equation. So that's a free boundary equation. And because I'm a mathematician, I think I have to kind of write you the equation nonetheless. So this is the equation if you want. You don't have to worry about it, but just in a nutshell here, this is your domain here. So in the domain, you constant. And the key is to say like how the boundary is evolving. So typically, maybe you know an example of like mean curvature flow, for instance. So mean curvature flow, what's the boundary is moving here, you look at the curvature, and that tells you how fast you're gonna move. Slightly different here, because the way you're gonna evolve here is not because of the curvature here, it's because here of the growing factor. So the more cells you have here, the more they're gonna push. So actually to deduce here how the boundary is evolving here, we need to couple that with so-called elliptic equation. That's a little bit technical, but at the end, whatever here is the division here happening there, that's what drive actually the push at the boundary. And so that's, okay, we can derive, it's not necessarily easy, and okay, but let me just show you that at the end, like it works. So let me just show you here. If no, it doesn't work, it doesn't want anymore. Okay. So here, for instance, that was a simulation I just solved with the cells as before, and now I'm solving the free boundary problem. So in red here is much simpler. It's just my PD is evolving. In green, it's actually quite costly because you have to solve all these particles moving. And it's kind of match, well, kind of, okay, there is some difference, but that's kind of expected. Finally, so we should go to oncostream. And oncostream, the way we model that, we just put the two previous models here and mix them together. So you take here this idea about correlated random work. At the same time, you want to not occupy the same space. You put that together, and this is what we're going to get to oncostream. So the idea here in terms of equations, similar idea here, we have the self-proportion here, and you want to kind of push each other out. The key is that instead of modeling, as Pedro pointed out, cells as just round, we put as an ellipse. So if you're on an ellipse here, if you want not to occupy the same space, you cannot just push each other out, you also can turn. And this turn here, instead of being like alignment, like I don't know if you're familiar with flocking model, we just have look around and see, oh, where are they going? Let me align, which doesn't really make sense for cells. Here they align because of this shape. So here they push each other out while pushing, actually, that's what creates the alignment. And let me, because my time is up, so let me just finish maybe with this one here. So let me just show a simulation, for instance. Oops, no, it doesn't want to show me simulation, so maybe. So same idea here, they push each other out, but this time here you have also like a direction. So on the left, it's exactly the same model, we just change the shape. So on the left here, they're not going to align because there is no like ellipsoid shape. And on the right, let me go a little bit further in time. At the end here, because again, there's no alignment per se, they just push each other out. Because of this shape, you create this kind of flock. And just to finish, that's really because we don't know here in terms of analysis what will be the macroscopic equation, but just to show that the other effect we end up seeing, I mean, not me, that's Sarah, actually, my PhD student, shows that the density plays a role. So if you have put a lot of cells together, then you start to have so-called oncostream, meaning here, instead of going just one direction, they can go in both directions. And so it's not just a flock, but really a stream that you can get from those simulation. And I'm seeing that time is up, so I'm going to stop there. Thank you for your attention.
Any questions?
Yeah, I just wanted to show the direction. Let's see. So that's what you get if you just run them, but okay, let me stop here, sorry.
Very cool. I was wondering if you've seeded both the spherical cells with the elongated cells and how there could be competition between those two cell types, so to speak. Thinking about the previous talk, when you see the existence of oncostreams and non-streams. So why would there be coexistence between those two populations?
So that's probably more a question to Pedro, but
Yeah.
if I remember the experiment, so the key is that what's happening is that when you have elongated, they tend to diffuse faster. So that probably also helps them to spread more.
Yeah.
In terms of competition, I don't know what will be the game here. But
Yeah, very cool. I love it.
Thanks.
Awesome.
So in the repulsion that comes in, right, from a biological perspective, it comes from the properties of the cells, right? I mean,
just it's matter, right? You cannot just not necessarily
right, but I mean, cells are different, right? So you can have stiff cells, soft cells, viscoelasticity, all of those, right?
Okay.
And so that's where the physical origin of that parameter would probably be in the physical properties of the cells, how sticky they are to each other, how elastic they are, and so on.
Yeah.
And how do you reconcile what is known about the mechanical properties of cells to the need or the assumptions that you need in the model for them to stream? Because, and the reason I'm asking this is that tumor cells, a lot of cancer cells, even in glioblastoma, the cells themselves are softer than normal cells. That means they are easier to squish, right? So they're not going to push as strongly back. And if you make them push less, then you're going to have harder time actually making them stream in some sense. So
I didn't show that, but of course you have parameter in the model, so you can always tune that in terms of adhesion, etc. That would be, yeah, I guess, experiment dependent, but you can always tune the parameter to consider different kind of property of the cells.
yeah, I think
Whether
it would be cool
most
to
relevant-
explore that space, right? What different parameters can
Yeah.
do.